Yesterday we took our multi-force problems to a new level. Yesterday we looked at what we call inclined planes. They're really a fancy name for hills. The hill or the inclined plane looks like this with a certain angle. Doesn't really matter what it is. We'll call it theta right now. There's an object on that hill that will slide down the hill. In the absence of anything else, it will slide down the hill. Now, why does it slide down the hill? Most people will say because of gravity, right? And yeah, that's partly true. But if it was just gravity, it would go where? Straight down. Not down the hill, but it would go straight down. So it's partly gravity, yes, but it's also partly the normal force that causes it to go down the hill. Yesterday we drew our free body diagram where we had the force of gravity acting straight down. We also had a normal force acting, and this is where we had to be really careful with our diagram. The normal force acted at 90 degrees, exactly 90 degrees to the surface. How long did it go? Well, we could keep drawing it forever, but how long should it go? It should go long enough such that the combination, these two forces, the F parallel, the combination of Fn and mg, the force of gravity, have to be exactly perpendicular to each other. So gravity is easy, right? It's always just drawn straight down. We're always going to nail that one. The normal force, we have to be so careful that we draw it 90 degrees to the surface and that we draw it the correct length. The correct length is such that F parallel, which is the combination of the two, the red one here, has to be 90 degrees to that normal force. Now, what angle is this right here? It's always the same as the angle down here. It's going to be theta. Now, at this point, whether we have more forces acting or not, we've got to find F parallel. F parallel would be, well, it's the opposite side of that triangle, right? Here's the angle, here's the opposite side. So we're going to say sine theta is equal to opposite F parallel over m times g. That's our force of gravity. And we can solve for F parallel that way. Equals m times g times sine theta. And then we do our thing, right? We can label F parallel right here. Not that it's in two places, but that we're just labeling it in two places. And then if we happen to have more forces, we can label those ones as well. However many other forces we have, and then we just do our thing with the F net is equal to the sum of the forces, similar to what we did on the quiz. So once we get F parallel, really, this is the quiz question, right? Like once we get F parallel, it's the same thing as what you did on your quiz just 10 minutes ago. All right, let's take a look at our homework questions. We had questions 1 and 2 on page 175. We'll put what we just reviewed into action here with checking over our homework here. Do you want to go over one of them or both of them? Do you want to go over both or one? Both of them? Okay. All right, number 1 says a loonie of mass 7 grams. Didn't we go over number 1 actually? No. Rings a bell. Did our example have a loonie in it too? Okay, so it's a different question but just similar. A loonie has a mass of 7 grams. I'm going to circle that because as well because I want to draw attention to the fact that we're in grams here. Somebody asked me on the quiz, do we use grams or kilograms? What's the answer to that? Always use kilograms, right? If you take chemistry, sometimes you get a little bit mixed up there, right? Because in chemistry you use grams, right? Okay? It's just one of those things. In Math 30 you use radians. In Physics 30 we use degrees. Okay, we just gotta try to keep that straight. A loonie of mass 7 grams is taped to the top of a toonie whose mass is 7.3 grams. The combination stays at rest at an incline of 30 degrees. What's the force of static friction acting on the face of the toonie in contact with the incline? So this is actually kind of worded kind of weird, but in the end, our loonie and toonie here is basically one object with a mass of 14.3 grams. Now, we don't have to do anything else. Like, we don't have to treat them separate. The loonie is on top of the toonie. We want to find the force of friction that is between the toonie and the hill. Let's make it a single 14.3 gram object. All right, we got an angle of the incline of 30 degrees here. We don't know where to go from here. Yes, you do. Yes, you do. Draw a free body diagram. We know that we have gravity acting down, which is m times g. We also know that we have a normal force acting exactly perpendicular. And how long should I draw it? Well, draw it so that F parallel ends up being exactly perpendicular to the normal force as well. Let's label F parallel up here. Do I have two of them now? Are there two F parallels? No, there's only one. I've just labeled it in two different places, right? I'm going to use the one on the bottom to actually find it, and then I'm going to use the one on the top to do my F net is equal to the sum of the forces thing. Do we have any more forces acting here? Yeah, we got friction, right? That's what you're trying to find. Of course you've got friction. Which way does it act? F parallel is the normal force and gravity combined, and it's bringing the Looney Tooney combination down the hill. Well, then friction is going to act to oppose that motion, which means it's going to act up the hill. So I'm going to label that up the hill here. What do you know about friction and in the F parallel here? Or what do you know about their values? They got to be the same. If it's at rest, okay, it's static friction. Static friction, it's at rest and it's staying at rest. Otherwise, it wouldn't be static friction. Then the forces have to balance, right? So that means that if I want to find the force of static friction, all I got to do is find F parallel, and it's going to be the same value. I think it was Jared that was it you, Jared, yesterday that was talking about something similar to that? No, Patrick, I think it was. Sorry? Yeah. Look, guys, if you don't notice that, if you don't notice right away that F parallel should be equal to the force of static friction, that's okay. Because at this point, we can still say F net is equal to the sum of the forces, F parallel plus FF. MA is equal to F parallel plus FF. What's the value of A? If it's at rest, A is 0. 0 is equal to F parallel plus FF. So F parallel, you can see here, would be equal to the negative of FF. We do need to find F parallel. Actually, I should have done that already. Let's say sine 30 degrees is equal to F parallel over m times g. Let's find that by saying say 0.0143, that's kilograms, right? 14.3 in kilograms times 9.81 times sine 30. 0.07014. We sub that in here for F parallel. Take it to the other side, ends up being negative 0.070 newtons. Is that right? Oh, wait a second here. I have made a small mistake here. It's actually not even, I made a mistake, but we could have covered for it because it could be right. It's still right here. I just kind of got lucky with my mistake. What did I miss? What did I miss that I usually do? F parallel is the force that acts down the hill. So what do I usually make F parallel's value, Ben? I usually make it negative, right? Which makes FF positive. And that makes sense because FF is which way? Up the hill, right? Now, if I had made F parallel positive and defined down the hill as positive, that would have been right. We just have to recognize in that case a negative answer means up the hill, right? Kenzie? F parallel came from some trigonometry up here, right? We have a right angle triangle.
I understand.
Okay, and this is our opposite hypotenuse, so we use sine theta, opposite and hypotenuse. Okay. In order to get that, though, it's so critical that we draw this free body diagram correctly. If we draw it like, here's what a lot of people do. I've seen this so many times, even after I emphasize those things that you got to watch out for. I see this so often. Oh, come on, it's not that big of a difference, is it? Well, the problem is if I do that, if I draw it that way, then it becomes tan theta is equal to opposite over adjacent, and I'm using the wrong trig function, right? So if you draw it wrong, you're going to use the wrong trig function. That's why it's so critical that you draw this like this so that you get the correct trig function, right? We talked about that quite a bit yesterday, right? Those two things you got to watch out for when drawing the normal line. A, that it's perpendicular to the surface, and B, that it's the right length. Okay, let's take a look at question number 2. Man, they really like their money questions here. You get the feeling that a bunch of people got together and wrote this book, and there is always a bunch of people, but you get the feeling that when they got together, they said, hey, you work on some practice questions for this topic, and you work on some practice questions for this topic. And the guy or the girl that was working on the practice questions for this just didn't feel very creative and just kept using the same context of money, right? Says a loonie of mass 7 grams placed on the surface of a rough book. The force of static friction of magnitude 4.4 times 10 to the negative 2 newtons acts on the coin. What's the maximum angle at which the book can be inclined before the loonie begins to slide? It's not a trick, but it's a good one. Let's draw this out. Okay, so just like you, I see questions sometimes where I'm like, I don't know exactly what I'm going to do. So I always start with what I know. What do I know to do in one of these inclined planes questions? Draw a picture, draw a diagram. Here's my inclined plane. Here's my loonie. Its mass is 7.00 grams, although I want to convert that. I don't know what the angle is here. That's okay. The maximum force of static friction, let's say if we're at the maximum angle, then we're experiencing the maximum force of static friction. So we're going to say, actually, let's make that another color here. Okay, I'm writing that down because I know it. I know that gravity acts straight down. I know that the normal force acts 90 degrees. Make sure, though, that F parallel is 90 degrees to that. Agree? Is that okay? The point where it begins to move, like just before it began to move, it was at rest and the forces had to balance. So once again, we would know that F parallel would be equal to the force of static friction. Therefore, we would know that F parallel is equal to what? We don't actually need to find F parallel here. Right? We know what it is. It's equal to static friction. Now, this is theta. This time what we're going to do, instead of saying sine theta is equal to opposite over adjacent to find the opposite side, this time we're going to say sine theta is equal to opposite over adjacent to find the angle. So sine theta is equal to F parallel, which is usually the one we're trying to find, divided by 0.007 times 9.81. This is where you guys that don't like trig start having a little bit of trouble here. We're going to say 4.4 times 10 to the minus 2 divided by brackets 0.007 times 9.81. Okay, there's our number. So I solve for theta there. Yeah, we've done that before, right? We've done that before with vector analysis. We say the inverse sine of that, oops, the inverse sine of that number, 39.8 degrees. Is that all right? That's trickier, right? Number 2 is trickier, but there is zero reason why any of you should have nowhere to start. And I'll tell you what, if you just don't get scared of it, like you're probably going to finish, you're probably going to get it. But you at the very least can get a good start on this question, even if you can't quite get the answer. Let's have a look at our force worksheet now. The worksheet that you've been working on for a couple of days now. Questions this time number 10 to 14, also on inclined plane or hill problems. All right, I want to take a look at question number 12 here. 10 and 11 are real similar to what we did in our practice questions. 12 is a little bit different than we're finding the force of friction here. 13 is different as well. In fact, 13 is a little bit harder than 12, but if you can do 12, you're probably going to be okay with 13. So we'll do 12, and then I'll leave you with the rest of them here. Number 12 says find the force of friction. We have an acceleration. Usually we're trying to find that. That's all right. Don't think you have to do something drastically different. Like, have we solved? I don't think we've solved a question for the force of friction in this context. That's okay. We still do the same thing. We have gravity acting down. So write that down. We have the normal force acting at exactly 90 degrees right here. And it's the length to make this F parallel exactly perpendicular to the normal force right there. Now, don't forget, I also draw F parallel right here. I draw it in 2 places. Even though it's not really in 2 places, I'm drawing it in 2 places. Which way is friction going to act? If it's accelerating down the hill, which way does friction act? Opposite, up the hill. So let's label FF like this. Notice I've drawn FF smaller than F parallel. How come? F parallel takes it down the hill. FF counters it, but it's moving down the hill. So which force is bigger, the force down the hill or the force up the hill? Force down the hill. So friction's got to be smaller, right? Okay, let's get F parallel. Why? Because this is what we do. Like, what can we do at this point? Get F parallel. So let's do it. Let's say sine 30 degrees is equal to opposite F parallel over hypotenuse, which is m times g. Let's say F parallel is equal to m, which is 5 times 9.81 times sine 30. We do that math, and that works out 5 times 9.81 times sine 30, I think is 24.525, I want to say. Is it? 24.525 newtons. Now what? Now what? Mackenzie, now what do I do once I have this F parallel thing? Yeah, what equation? F is equal to m times a, but also F is equal to the sum of the forces, right? F net is equal to F parallel plus FF, and then m times a is equal to F parallel plus FF. M is 5, A is negative 3 because it's down the hill. I'm going to say it's negative. F parallel is negative 24.525. We solve for FF. Get the number on the left side. Take the 24 over by adding because it's a negative. Solve for the force of friction, yeah, and it works out to be 9.5 newtons. Hey, guess what? It's positive. Should it be positive? Yeah, it's up the hill. It's up the hill. If I defined negative as down, then this should be positive.